Bismillahirrahmanirrahim. Welcome to Easy Learn, and this is network analysis, and this is the episode 21. And today I had decided to discuss the whole discussion on the soft. Wow, oh my God, I forgot about the software. Smooth draw. Sorry, smooth draw. This is our board, and I will try to write here, but unfortunately, still we don't have the hands-on on our new platform, that is the pen tablet. Still it is missing. I will try to make sure that its deficiencies uh, fulfilled with my better compromisation and dedicated hands. Anyway, our today's episode is 21, and I will try to discuss today's lecture with starting today's special chapter. A new chapter is going to start, and the name of the chapter is the network equations. As the name suggests, these chapters that it is going towards the discussion of the networks. We are moving one step towards the networking. Before today's lecture, we can say we have discussed almost every type of active elements, basic elements, passive elements, like three major discussions active of passive elements, physical phenomena, field interpretation, and circuit interpretation of inductor, capacitor, and resistors. So the almost unit scaling, derivations, and these concepts are, it's not time to utilize these concepts in the Kirchhoff laws. So we are ready to start our today's discussion with Kirchhoff laws. Before going to discuss, did you have in your mind about the network equations that we used by the Newtons in I think episode 10 or 10 to 15? I used the equation in chapter number 1 that are actually derived and used and based on the Kirchhoff's laws. These laws concerns the algebraic sum of voltage around a loop and currents entering or leaving a node. So because these laws are based on loops and nodes, so why not we first discuss again, once again we discuss these concepts, so that our discussion will run smoothly and without any difficulties. First of all, I want to highlight some basic things, and the first thing that I wanted to show you here is what is a loop. For a loop, let's say this is what we have right now, and this is voltage source, and if this voltage source is connected with some resistive material here, and when it is going through this process and we close this path, so that circuit will continue, and the path is closed by closing its path. This is a simple resistance that is connected in series with this voltage source, and when closing this switch or circuit, there is a path. You can see now the path of the current that is going to flow in this way from let's say positive towards negative. By the way, there are the two types of the current. First one current is the current that flows from positive to the negative, and we call it as a conventional current, while CC, not the CC of your YouTube videos, that means the subtitles, but here the CC means the conventional current. While if we discuss the current that flows from negative towards the positive, and we call it as a real current, or sometimes we call it as electronic current. Actually, this is the real current, that is the flow of the electrons, but usually more of the cases we discuss this current, and until we specify that we are using the electronic current. So all the directions here are following the positive towards negative means conventional current, and as you can see, I am showing here the from positive towards negative, so the current is flowing through this whole process, and this is the only way to complete the path. So this is a concept of the loop concept. Loop means a complete and a closed path. Whenever we have a closed path in a circuit, the loop is there is a loop from the point where we are going to start, and then we flowing through and passing through all the passive and active elements. We reach again at the point, then we will say and call that this is a loop. A loop is doesn't means that there must be an active element, or there must, if this is also a loop, there must be a flow of the current is necessary. This is also a loop. The current can flow through this way and this way also. But when we have this type of the discussion here, means another loop, as you can say, when we will call this one as a first and this one as a second, because there are more than one loops in a circuits are there, and there are sometimes sub loops are also. When sub loops means that there is a major loop and then further loops can be seen in this loop. And right now we are only interested in the loop, that what is a loop. So now we are ready to discuss the second concept that belongs to nodes. Nodes, actually nodes are a junction, and the junction come into the contact when we have one or more active elements that are joined. Definitely there must be two elements to connect with each other. When it is not necessary or specified that there two elements must be the active elements or passive elements. The only requirement is the two elements. For example, if again I am going to use this type of the circuit like here, and if we have a resistance here, and suppose that this is a point, so we can say that this is our first element and this is our second element. I know this is an active element and this is a passive element, but between this there is a junction, a point that separates these 2 points, or there is a point of the connection. For example, if we use a different color to specify that this resistance, this is a resistance, so a different color is used to specify that this is a resistance. A different color can also be used to specify that this is a voltage source, and this is a voltage source. At this point it ends, its terminal is going to end. No, there is a connection required between these two colors. This connection is provided with this color, and we will call it as a node. As you can see, this is a node. So a node can also be represented here, here, and here. So what does it mean? It means there must be a junction that we can say this is a node. Or this is a, in this circuit, as you can see, the resistance is here, there is a resistance, there is a connection between these two of them. And if we can say, according to this logic, if we say that this is a node between this resistance and this resistance, no, this is not an exact good node. If we have a circuit in this way, that further splitting, like here you can see the current is coming here, and splitting is done at this point. You can see one from first there is a one wire coming through, and then at this point we have seen two more wires emerge. What does it mean? We can say that this is actually our node. Not like using this logic we say this is a node and this is a node. No, we can say that this is a point and this is a junction, and at this point the current which is flowing can be here split up like in this way or in this way. So there are the two priorities and options available at this because the path is split at this point. Now coming back towards after discussion about of the nodes and the loops, let's discuss a little bit about the series and the parallel circuits and the logics about the voltage and the current. Although I already discussed these things in the previous lectures, but as a matter of the time, you may some students may be new to join here, and so that again repeating, because we have, if you already know about these things, then you can definitely skip this portion and go through the next portion. Okay, so this is a third point, and where we are ready to discuss the series and the parallel circuits. Series or parallel circuits. What does it mean, series and parallel circuit? First, we discussed a circuit that is a series circuit. Here you can see, if I use a resistance, again, because this is the most simple circuit for me to use in any case, this is a series circuit, and we have here any type of the source, not mentioned what type of the source actually I am using here, but for simplicity I'm not writing here anything, but let's say the current is flowing through this way. As you can see, the current have only one path to follow, and if current is flowing through this way, it has to pass through resistance, first resistance and the second resistance. It doesn't happen that current have wants to complete its path, but it doesn't want to flow through R1 or R2, because there is only one path and the resistance comes through this path. If the current wants to complete its way and make sure that this is a loop, there must be a current into the resistance. So we can say the resistance, both resistors are connected in the series. So in this sense, we say that the voltage that is flowing through them is split up. For example, here we have a positive and negative. We will call it that the positive here coming and the positive reaches here. So this is our positive and this is our negative. And the positive at this point, this is our positive and this is our negative. For example, we say that we are using our 10-volt source, because there are the two things, one is the current and the second is the voltage, and these two things have always opposite type of the relationship with each other. Whenever we say that our voltage is not ready to split up and the current splits up, while when we discuss the parallel case, the case will be reversed. So if you remember the one case, it is very good thing that we automatically remember the other options. Like here, in case of the series, it is very easy to remember that this is our current that is flowing and there is no other path, so current is not divided. So current is not divided. The whole current in this scenario will remains the same. So in these type of the circuits, like series circuits, we don't need to calculate the current. Why? Because the current remains the same, and in the voltage laws, and we need to find the voltage, not finding the current. Current needs to be calculated when there is a parallel combination is seen, because in parallel combination the current splits up. So we can say here the summary, that the voltage split up or divide, while the current remains the same in case of the series. Now it is the time to discuss the other circuit that is called the parallel circuit. Again, I am simply using any logical active element, and if we connect this time, this is a resistance, and this time I use a different scenario. I am using an active element. You can see here that this one is our active element, and this is our first resistance, this is our second resistance, and this is our third resistance. And if current flows through this way, there is only one path to flow. It means that this R1 is connected in series, because there is no other path to flow, and we can say current I, when needs to complete the path and the circuit is to be in connected state, there is only one path till here. Then we have seen that there is a node and current needs to be split up and decided, either it has to choose this way, or it has to choose both ways. like some portion of the current comes to this way while the other have to flow this longer way and choose this other destination, choose the other transportation and the other tracks to complete its destination. So in this scenario, if we say that this is our current, and here we definitely need to define the current as I1 and this current as I2, because current splits up. So there are the two multiple options, and if we remember only first, like the series circuit, the concept of the series is in our mind, then definitely a parallel automatically comes is memorized, because you just need to reverse this. In the voltage in case of the parallel will be same, while the current is divided. You can see the current is divided and here the voltage is divided. So there are the two options. You need to be kept in your mind this concept, that as this is very important in our discussion. So the algebraic is used to indicate that we take into account reference priorities and reference directions in the summations. We also introduce in today's lecture about other reference in the form of the positive direction from traveling a loop and choice of entering or leaving as positive for the current summation at a node. So this is just an introductory part and the highlighting of the different previous concepts. Now moving towards our most important portion, and that is starting about the Kirchhoff's voltage law. Remember, there are the two laws, Kirchhoff voltage law and the Kirchhoff current law. So Kirchhoff voltage law states that the algebraic sum of all branch voltage. So here the word used is the branch voltage. So whenever we are you are confusing and messing with the word branch, you need to go back into the previous episode so that you may come to know that what is a branch. For just sake of the recap, I'm just here telling you about the branch. For example, we have this type of the circuit, and the branch means that we need to define the nodes. For example, this is our node and this is our node. We need two nodes, but the active element is replaced with single wire. And if we have a very sophisticated and dedicated graph, then we will need to represent an arrow on this graph, and this arrow can be either on this side or this side, depends upon the voltage polarity. And then if we use these type of the symbols on it, then we will call it as an oriented graph, and this branch will need to be remembered by the words oriented branch. So this is the branch, what I mean in today's definition, that Kirchhoff voltage law states that the algebraic sum of all branches around any closed loop of a network is zero at all instant of time. So this is the definition of the Kirchhoff voltage law. You need to be very specific when defining these rules and regulation. For example, if we go and define, it is a consequence of the law of the conservation of the energy, that energy can neither be created or nor destroyed. For example, let's say we have a circuit like this type of the circuit here, and this circuit can have a positive and negative here. Then we need to connect, and this is our point, any point. For example, this is a point A. We say that this is our A point and this is our B point. There are the two different points that can be seen, and if we say that this is our A point and this is our B point, and then if we have a resistance here, and then definitely a junction between the two elements, and we will call it as a point C in our circuit. I am here adding another resistance to verify the Kirchhoff voltage law. There are more than one resistance in this graph, also in this network, because this is a one illustration of the Kirchhoff voltage law. There are other two to define and explain the laws. One second. So this is a point A, this is point B, C and D. Actually these are not points, we will call in our terms these are the nodes, and nodes are really very important. The nodes plays a key role in all the discussion. This is the branch that I am using to highlight in a different color. This is a branch from one node to the other. We will call it as a branch 1, and this is our second branch according to our point of view. This is third, and this is so on. There are the different branches that can be seen through this way, but not interested to use this in our discussion because it may be very lengthy and chattered when we write here in this way. So removing all these things to make sure it looks like a very simple circuit. Okay, this is a time varying source, so I am ready to use the VG here because the time dependent or a time depending source are VG, and this is our resistance, and if we call this resistance as R1 because this is the first resistance, second resistance, and this is our third resistance. First of all, let's define a loop direction. How we can use and define the loop direction? Very simple. Just consider this positive and negative. This positive here is toward upper side, which means the current is ready to flow in this direction. And when we follow this path, you can see the current adopt this path like this way. And it means that if we follow this according to our conventional current, we say that this is our loop direction. So this is our loop direction, and this positivity here, you can see positive is coming and positive reaches here. So this is the positive, and from negative on the opposite side coming from this side and reaches here, here and here. The positive reaches here, at here, and at this point also. So this is how we can say the positive and negative polarities are assigned at each different terminals. So this is the one way to represent all these things. I am using a simple resistive network for the simplicity. These are all passive elements, and there is only one active element. Now it is the time to understand that this is a series circuit, and in series circuit you know that there is always a voltage split while the current remains the same, because there is only one path of the current to flow. So when voltage split, we will write here there is a different voltage can be seen at this point, there must be a different voltage at its terminals, and there must be a different voltage across the R3. So different voltage can be seen and can be recorded through different devices across these different resistance. So we need to define different voltage, like this resistance across the R1 is the V1, resistance across R2 must be V2, and the resistance across R3 should be R3. Now it is the matter of the time to further start the further discussion. Now we are considering a unit charge that is placed at the node here, and let's suppose highlighting the unit charge with a very aggressive color red. I'm just kidding. Unit charge placed at the node A in a network. We will move this unit charge from node A to node B. We are ready to move this unit charge towards the B. What we do here, we want to move this unit charge from point A to point B, and from point B towards the point C, here towards point C. All we need to do here, then continuously move the unit charge towards point C, and then we want to move this unit charge from D to next onward, and then reaches back from D to all the way back to point A from where it started. So this is the first discussion of the Kirchhoff voltage law. We want to move this unit charge. So this is a overall a loop, complete closed path, and the direction can be seen and very closely from here, and the overall direction that is the overall voltage in this loop must be same. As you know, the voltage split up. This is the first voltage, this is the second voltage, this is the third voltage. We know the voltage is going to split up across the R1, across the R2, and across the R3. But what do we want here? We know voltage split up, but the overall voltage that is provided by connected VG in this circuit must be the same. There is no options to that the voltage is increased. For example, if we say that the voltage is the 5 volt here connected, as we say that the charge or the energy that we use to represent here with the help of the dot is 5 volt in this circuit present here, then there is no means that the energy can be created in this loop. The energy will be destroyed in the different options and different ways. Energy can neither be created nor destroyed, and this is the law of the conservation of energy, that voltage being the energy here, and or the work per unit charge, if you remember. And each time we will determine the energy lost or gain. For example, when we move through point from A to B, we will determine that our energy is lost or gain. As you can see, there is an active element, so definitely energy will be gain or loss. So there are the two terms, gain or oh my god, I'm not able to write here actually with this mouse. Now, gain or loss, these are the two things that we need to keep in our minds when we move from one node to the next node. So if we tabulate all these changes for the various moves against assigning a positive number for a gain, and let's suppose a negative number for the loss, like here if we move from point B to point C, the energy will be the lost, so we will assign the negative V1. For example, if we assign the positive for the gain, then negative for the loss definitely, and again if loss, then there are more than one active elements can be seen in a circuit and network. As we already discussed in the previous discussion, in the previous episodes, there are maybe the controlled type of network elements that are controlled through other locations in a network. So at any points there are more than one energy gains can be seen in a network, but overall in a loop the energy must be the overall energy must be zero. That means that the net energy is zero. The energy can neither be created nor destroyed, and this is what we are ready to see. But before proceeding, let me tell you one more thing. An increase in energy in going from point A to point B is definitely as a voltage rise here. From point A to point B is the voltage rise, while a decrease in energy is the voltage drop, which we call here as a voltage loss. So we can define the voltage law, Kirchhoff voltage law, in terms of different forms, like here voltage drops and voltage rises. Around any closed loop like this type of the loop, at any instant of the time, the sum of the voltage drops must be equal to the sum of the voltage drops is equals to sum of the voltage rise. We can say the gain must be equal to the loss. So overall there must be zero. Like If we using this diagram and we want to define different steps and using very simple resistive network, the voltage reference direction assigned to the elements and a clockwise loop direction you can see here. And remember in your mind, then whenever we wanted to define and assign a specific voltage direction, we will call it as a either clockwise or anti-clockwise. We will not say that the voltage is going from positive to negative, or from left side to right side, or right side to left side. This is a wrong way. Actually, in a loop there must be a clockwise or anti-clockwise movement, and anybody who knows electrical engineering a little bit about the networks can easily understand about your logics. Okay, now coming back to word again, what I am discussing. Then we need to define some voltage law, starting with the node A. Now let's start. We have a node A here. We assign a positive sign to the voltage if the polarity marks occur in the order positive to negative. Let's say this is our starting point, and we will assign the positive sign to all those elements. This is what I decided. This is the what I decide as a reference. This is up to me. I can decide whatever I want. This is up to me to decide a specific criteria, and I decided the criteria is that I will assign the positive to all those elements. This is the first element, this is second, third, fourth. There are 4 elements in this complete loop. So I had decided to assign a positive element, so positive sign to those when positive sign comes in front of me. I had decided to assign the positive number the first. Okay, let's start with the equation that is for this voltage loop. So for this loop, starting with the node A, we assign a positive sign to the voltage with the polarity marks occur in the order positive to negative. As you can see here, the marking order is negative and then positive, because we are achieving this target from this side, like from this point. So first in front of us, this what does first come? Negative. So we will use it as a negative mark, because if the positive comes in our way, then we will taken it as positive. So first one is the negative sign first, and then the name, that is VG. Then next, moving next here. So this is the next point. What does the sign telling us? Sign tells us this is a positive. So, and what positive? That is the element, the name of the element, that is the R1. R1? No. We are interested in voltage. So this is the voltage, that is V1. So positive V1. The what next? They're moving, and then we can see there is a positive again, and now this time there is a V2. So we will use the positive V2. Then again moving here, and you can see again the positive in front of it, because we are moving in this direction, we are following this direction. So again positive, and this time V3, here V3, and the sum of all these is must be equals to 0. That is what I was saying according to the law of conservation of energy. The sum of all these things, there is a one source. And if you look at this very closely, you can see there are the 3 elements that having the positive signs, while one have the opposite polarity. You need to be kept in your mind that the one that is at the active element will always have the opposite signs. And if you look at this equation, by chance if I write mistakenly this as a negative, V1 negative V2 plus V3, then definitely we will easily understand that how this will be an active element. Going to the V2, you will understand that you by mistakenly write it as a negative when you look back to the original position of the V2 and track down it. So this is the exact way and easy way to understand. So the one sign that is easily can be seen here, that this is only the one and only active element, while the others are the consumers or the passive element. Now this equation doesn't looks very good and very nice. So what does we do here? If we want to interested in calculating v1, v2, v3, or we want to interested in active separate with the passive separate, what we will do here? There is one way, an easy way to move these to the other side. So it will also be the positive, means the source on the one side, the passive elements on the other sides. If it goes to the other side, what does it become? It will be Vg with a positive sign and the other elements as it is. So this is a very basic and the simple representation of writing the Kirchhoff's voltage law. This equation is interested as a this equation is interpreted as the sum of the voltage drops being equal to the sum of the voltage rises. In talking about rises and drop, it is conventional to have a reference node, or we call it as a datum node. I will also write in the lower thirds of my video what is the datum, actually DATUM node. That means a reference node. Reference node is very important in discussion. A reference node, what is a reference node? Let me tell you and explain you what is a reference node. For example, here if you look here at this side and I draw, for example, a no, I want to use and indicate here a simple ground. This is a ground and we need to represent this ground with G here, and this plays a reference point here. In the networks and networking, we need to show our elements with respect to some reference, and when we use and highlight and remember the nodes, there must be a reference point. And you can see this is our node here in this very simple and basic network. This is our node that I highlighted here. So this is a node, or we call it as a reference node or datum node. Why we call it as a reference node? This reference node will be our reference node because this is very necessary. Why it is necessary? In some way that we take about the as you know, when we go and into the mountainous region or a very at a region that is belong to a heights and a very high region situated at a height, then how we can call that it belong to such a height, it is situated at high heights of, for example, 500-meter high, with what reference we compare the heights? We compare all the heights with the sea level. We call that we are about 500 meter above the sea level, 1000 meter above the sea level. So this sea level is our reference, that being reference for the elevations. So in talking about the voltage, we select a reference that is the ground, which is indicated here with the G, you can see. So if I used again positive negatives and positive negatives, and there are the two nodes, for example, this is a node A and this is our node B, then I will definitely call that the node A is at a higher potential with respect to the ground, while the node B is lower than the ground potential. You can see this is the lower terminal because it is with towards the negative and it is towards the positive, and the ground is in the center and it is towards the height and it is towards the ground. It doesn't mean that actually the direction matters. Actually the matter is the polarity. Got it? So this is the one way. So Kirchhoff Current Law. Now want to discuss the Kirchhoff Current Law, and with the short form of it is the KCL, Kirchhoff Current Law. Kirchhoff Current Law is just like the Kirchhoff's Voltage Law, same and not much difference with the Kirchhoff's Voltage Law. Kirchhoff Current Law states that the algebraic sum of all the branch currents, so there must be a branch. So why not we first use the branch, but let us first discuss the definition that algebraic sum of all the branch currents. This is our branch. Let's suppose branch current leaving a node is 0. Leaving a node is 0. Leaving a node current. Our current that leaving a branch crowd must be equals to 0 I. Current at any node leaving a node is 0. This is a sophisticated definition. We can also define this in a simpler way also, that this law is a also consequence of conservation of the charge. Charge which enters a node must be equal to that is leaving, because it cannot be stored there. There is not a type of the battery to store the charge. So if we have this type of the circuit, there is a junction, we will call that there is a type of the node. So if the current that entering from this side, there must be if there are two paths or the three paths, let's suppose there are three different ways, then let's suppose 10 ampere current is entering to this node, we will call this node as N. And if 10 ampere of the current enters at this node, there must be the same current that exits to different branches through this node, because if for example 1 ampere current is exiting through this point, and 2 ampere from this point, 2 and 1 3, and then 7 must be entering through this point, to make sure that combination of the leaving must be equal to the combination of the entering. Entering is, that is, you can see entering towards node is the 10 ampere, while the leaving is 1 plus 2 plus 7. So if it is not equal, let's suppose this is not 7, and if we consider this as a, let's suppose 5 ampere, then there is some current that is missing. 5 plus 2 7 plus 1 8. So where is the 2 ampere current? Then we will say that 2 ampere current is in the node, which is wrong. The node cannot store the current, node cannot lose the current. This is a junction symbol. If it is losing the current in the form of noise, in the form of heat, or in the form of the sparking flashes, then there is a loss of the energy, and it is not following the Kirchhoff current law. So we need to take a consider on this, and need to keep our eye and reconsider all the points. Since the algebraic sum of the charge must be 0, the time derivation of the summation must be equals to 0. Like the voltage law, the Kirchhoff current law must be also stated in the other ways and a simpler ways. Like we can say the sum of the current entering a node must be equal to the sum of the current leaving the node. Thus, in terms of the assigned reference direction shown in this very beautiful diagram here, we can write our currents. Like for example, we call that this is our I1, and this is our I2, and this is our I3, and this is our I4. So defining again the equation for this type of equation, we can define our equation very nicely. Starting from this side again, different we can assign different nodes. Like this is our A, this is B, and this is node is our C, and this node is our D node. And writing this equation, we will simply use, starting from this point, that is entering is taken for example as a positive. Let's say we consider as a positive I1, that leaving is considered as a negative I2, okay, minus I3 is leaving, minus I4 is leaving. So all these three currents are leaving, so negative sign is assigned to all of them. while this is the current that having the opposite polarity to these other one, because this is the current that is behaving as a source to this node n. So the sum of all the currents entering a node, that is entering, that is the entering, and the sum of all the currents that leaving a node must be equals to 0. So this is the way we can define the I1 is so the we can also define the formula and rearrange in this way, that I1 is equals to the current that is entering a node is equals to I2 plus I3 plus I. What if we have another branch for the entering the current, means we have another branch that is helping in the entering a current also. Then for example I2, let's suppose we have an I2 that is entering the current into the node, and the 2 is leaving, 2 is entering, then there the I2 will come toward this side. Okay, then the positive sign is assigned to the I2 and negative to the I3 is. So this, in this way we can redefine according to our desire and our situation using this Kirchhoff current law. This is a very important, and you need to understand, because these two Kirchhoff's voltage law and Kirchhoff's current law are the basics of the networking. When we are applying the nodes, different nodes, different types of the equations, we need to define, and using this even in a 1 second and a 1 step, we don't have enough time and enough steps there to utilize. We have to, these are the ABC of the networking. These steps must be in our minds. So as an example of the application of the Kirchhoff's voltage law, we are going to consider a very simple network. So for the sake of the simplicity, I am again selecting a very basic and very simple network. And these two networks, like first one, if we define here, this is our point that I call that this is point number 1, and we are having this a resistance, and we are having an other resistance, and then this is our terminal. So this is number one first loop, or this is a loop. Actually this looks like open, but actually I'm just showing that this is connected to some one source, any source, that is the VA. Actually we are designing a source, not a source, I'm sorry, R1 and R2 respectively. And you can see this is a series circuit, and if the current, any current, like let's say the for this IA, the current is IA, the voltage is VA, the voltage splits up again. The voltage at this point is positive negative, as positive negative. The direction of the current is again can be seen in this way, and this voltage we will call it as V1 and V2 respectively. And if we have a PCB for designing the circuit and we haven't enough elements, like this is 2 resistance, let's suppose we have 3 resistance connected in series, and we want to make sure that the space occupied must be less. So if the 3 resistance are wasting our space, why not we connect only one? But what steps needs to be taken? There must be some measurements. We need to define a circuit with equivalent, we call that is equal to this circuit. So let's define another circuit that is equal to this circuit, but a little bit different type of different resistance structure there. Like this is terminal, very simple. This is replacing now this one, again a series circuit. This doesn't mean that I draw here vertically resistance, but you just take into consider that there is only one path of the current to flow. So it means there is a series circuit. Either I draw the resistance here or I draw the resistance vertically. It doesn't matter, but the main thing is this is again a series circuit. In a series circuit, whenever the current starts flowing, there is only one path. So all the discussion applies to it very consciously, and same discussion applied to it. So this time we say that the voltage that is the VB, again the voltage is same. We are not saying that we are changing the voltage. We just interested to replace this R1 R2 with this, and we call that this and this are the two equivalent circuits. So the voltage at this point is that is coming towards toward from here the current I. What is the current here? IB as the voltage here. Again the polarity is positive negative, and the clockwise direction, because the positive is upper side and negative is downside, and along this we call that V, simple VC, you can say VC to differentiate VB with this. Actually the VB whole is attached to with this one, there is no division further, so we can also write the VB here, because overall the VB is equals to VC, because whatever the voltage at the terminals is coming directly to the across this resistance. There is no other elements connected, but for the sake of the just for understanding, I'm just writing here. Okay, now it is time we wish to determine the conditions under which these two networks of the looks like and behave in a similar way. The two networks are said to be the equivalent at the pair of the, if the pair of the terminals voltage current relationship means the VA must be equals to VB and the IA equals IB, then we will call that these two networks behaves and in a similar way. For the network first and the network second must be in equal, and let's define the for the first network first, for the network 1. This applying the Kirchhoff Voltage Law. No need to find the current for this network again. Why no need to define the current? Why I am saying this? Because this is a series circuit, and in series circuit we are not interested in finding the currents, because the current doesn't dividing here. Only the voltage is that is splitted in the first across the R1 and then the R2, while the current remains the same across this network and across this network. So whatever the current IA, that is for example we have a 10 ampere of the current applied at the terminals, the 10 ampere reaches here, the 10 ampere reaches here. Whenever, so we just need to calculate the voltage, because the voltage is splitted. If 10 volt is applied at the terminals, there must be a different, for example 3 here or 4 or 5, but here V2 and V1 must be different. So we need to define specific voltage for these two different loops. Let's say for the first network we define here, that is the VA according to the KVL, what we already discussed in today's lecture. VA is equals to V1 plus, it's I'm just skipping first step, like this step, that minus VG is equals to plus V1 plus V2, and then in the next step I say that this equals to this. I am here directly using that the active element, that is VA, that is equals to R1, that is the passive element, or we can say V1 plus V2. In other words, if you are looking first, because this is our our first episode or today's lecture I described, and you haven't practiced it yet, for the sake of the simplicity I can also write in the other way, like in the conventional way what we discussed earlier. VA is equal VA, this is the first positive element, and then I'm taking it a positive minus V1 minus V2 is equals to 0, and then VA is here and the negative element is going toward other side, VA1 plus V2. So but next time, so the next time we are using the this equation directly, because this saves our time and it is very easier to write also. So VA is equals to V1 plus V2. Now we are not only using V and V. This is a not looks professional way. Now it's time to introduce a specific this is a resistive circuit. And if you go back to the resistive section of the chapter number 1, when we define some specific formulas for the resistive networks, there we discussed the exactly specified formulas for the voltage finding in terms of the resistance and the current formulas in terms of the resistance. I think this is I don't know about the exact episode, but I think this may be the episode 15 or 16. I think 15 maybe, when we highlighted the summary of all the three systems, and that is why I said that to keep in your brains and write it in your notebook's first page. So VA is equals to according to the formula of the resistive network, V is equals to Ri. Go back and look if you haven't in your mind, and if you have, that is well and good. So according to using this formula here, for the case of the V1, we can modify it according to our case R1 and I1, because current is same, so we are not choosing it because current overall same. So R1 and I1, but here the current is IA. For the V2 it is R2, and the current is again, current is same, current is IA. So this is the way to write this formula. Now we can use write this formula for the equation for the second loop also. For writing this formula for the second loop is again very simple. VB is equals to VC, because overall there is only one that is using this volt, this overall using the utilizing this voltage, and this resistance I haven't named it. This is R equivalent, EQ. So R equivalent, and by using the formula I can simply write I R, and R is the equivalent. So R equivalent, this is the way to write the formula. Here we have the I, that we use the IB here, and if you I want to share you some information that in our case, we, as I said in the start, that VA is equals to VB and IA is equals to IB, because we are deriving a specific relation of this circuit with this circuit, and for the comparing and make sure that these two circuits operate equally, we need to provide equal voltage to the first circuit and the second circuit. So I said that the same voltage is applied to the first circuit and the second circuit. For this reason, I am saying the equation that is this equation number 1 and equation number 2 are the same, because VA and VB is equal. So we can compare these two equations, because VA and VB is equal. So if VA and VB is equal, then the left, this side, this one and this one must also be equal. So R1IA plus R2IA is equals to IBR equivalent. So this is a way to write this equation. This is the first equation, right side, and if the left side of the equations are same, this means the right hand of the equations are also same. This is the simple mathematics rule. So here you can see we can define a one thing common, that is the R1 plus IA. IA can be taken common here, and IB from here And if you go back and look here, IA and IB are equal, so these two terms can be cancelled with each other because these two terms are the same. In other words, IB go to the other side and it will come here IB, and then again it is cancelled out. If this is a 5 and this is 5, and if 5 goes in the denominator of the 5, then definitely it will be cancelled out. So this is the way we can write these terms are cancelled out. So continued, this R1 plus R2 is equals to R equivalent. So this is a way to define a specific relationship. So what does this equation tells us? This equation tells us if we want to replace this circuit, for example, this circuit is replaced with this circuit first with the second circuit, we need to define, for example, the first resistance is our 5 ohm resistance and the second is 10 ohm resistance, and the 5 plus 10, then the 15 ohm of the resistance. By adding two resistance, we need the equivalent resistance by adding two resistance. The value of the equivalent resistance must be found by adding the two resistors that are connected in series. So this is also a general formula come in our mind, that we can also calculate, define a specific criteria is defined. Like the next time if we have a summation of the resistance for connected in series is equal to the equivalent resistance of the combination. Generalizing the result of this equation, we call that all the networks, for any network, the equivalent resistance if we want to calculate, because the next time we are not using this whole process. We will just know that for any network having the resistance connected in series, we are going to use this formula, that R1 plus R2. Just in case of the series, remember that in case of series circuit, not in parallel circuit. In case of the series circuit, if we have different type of resistance that are connected in series, just add them and you can replace them with the only one, and just continue this process until you have the Rn resistance. And generalizing this, we can also write that the summation of all the resistance that we have, all the resistance, and j from 1 to n, means that all the resistance, Rj means j, the value of j is from 1 to n, and n means, for example, 10 resistance, then n will be 10, and in our case the n is 2. We have the two resistance, so by adding the two resistance we can use this formula. So this is the generalized way. Now this is the time to end the discussion, and I will also, you can also try for the parallel combination. There are the different rules, just keep in your mind about the series and the parallel combination. I think we had discussed and spent enough time for the today's lecture without even a break. My throat is almost dry and I need to spend some time off the record and take some rest right now. Anyway, so I am leaving the KCL. Yeah, KCL means, because this is a parallel combination circuit of the inductors, I'm leaving the KCL to you, where this type of the circuit you can see like an inductor and an other inductor, two inductors that are connected in this way, and you can see the two inductors are connected, and L1, this is L2. The current entering here at this point, the current needs to be split at, this is I1, and the current that reaches here, that is the I2. So the current split up. So this is a way we can apply the Kirchhoff current. Remember that here again you need to use the formula of the inductor that we derived previously, and you need to be kept in your mind for the next time use also. That is the 1 over L integral V dt. and the range on the or the limits of the integration is not necessary to use at this stage. By the way, I will also give you the solution of this at the end of the video, means in the coming minute in the next time, because I'm right now going to just terminate the session. Next discussion inshallah will be continued from the next topic. Just keep watching. Watch, learn, grow. See you next time. Allah Hafiz.